Good morning, everyone. In this lecture, we are going to discuss about, DC to DC converter, or you can say it's a chopper. And this is the subject of power electronics. As you know, in previous lectures, we have already discussed about your converters, in which we discussed about your AC to DC converter. That is called your rectifier. So, in converters, we discussed about your single phase AC to DC converter, three phase AC to DC converter, and further we divided three phase converter into two parts, your bridge converter and midpoint converter. Okay, so in this lecture we will discuss about DC to DC conversion. As you know that DC to DC AC to DC conversion is called your rectification, and DC to AC conversion is called your inverting mode or inverter. But in this lecture, we will discuss about DC to DC conversion because in many industries and in many applications we require regulated DC, which can be uh, which can be converted by the help of chopper. Okay, so let's come to the point, learning objective and outcome. So after this lecture, I'm expecting from students that student will be able to understand DC to DC chopper, the different type of DC choppers, and their operation, and their waveforms. So student, after this lecture, student will be able to classify different kind of choppers and their applications, and their waveforms and operation principle. Now let's come to the contents. So these are the contents of this lecture: features, elementary principles, classification, principle of chopper, buck chopper, goose chopper, buck goose chopper, and different quadrant operations of chopper. So, chopper is a static device, that converts your fixed DC input voltage to a variable DC output voltage directly. Why this is called static device? Because in this chopper we are using static switches. It may be your SCR, it may be your BJT, it may be your GTO, it may be your IGB. So it will depend whether you require this chopper. So you are using a switch which is static, which has not any kind of movable part or mechanical part. That's why chopper is a static device, and it converts your fixed DC voltage into variable DC voltage directly. So you can compare this chopper by transformer. As you know, in transformer step up or step down the voltage, right? And Transformer is used to step up or step down the AC voltage. But in chopper, you can also use your DC to DC conversion directly. So you can get the DC voltage, fixed DC input voltage to variable DC voltage, and the output voltage may be less to your input voltage, or it may be your high to your input voltage. So it's like your AC transformer, which work as a DC transformer in DC. So it is more efficient than AC transformer as they involve in one stage conversion. Actually, it offers smooth control, high efficiency, fast response, and regeneration. We will discuss these points in our next slide. So chopper can act as a step up or step down device, DC device. Chopper can be operated in either a continuous or continuous current mode operation. Chopper can be built with and without electrical isolation. They find application in trolley cars, marine hoist, forklift trucks, and mine haulers. So there are many applications of chopper where you can use these choppers for DC to DC conversion. So what is your elementary principle of your chopper? So chopper is like you can compare it like a switch. When you are going to uh, turn on and turn off this switch, and this switch is your semiconductor switch. So high speed on and off of semiconductor switch, it connected to source to load and disconnect the load from the source at high speed, and continuous triggering on and triggering off at rapid switches speed. By varying on and off time of the SCR, the average voltage can be varied. Okay. So, it's depending upon the chopper can be classified in 5 parts, and the classification of this chopper, it's depend on the direction of your output current and voltage. So chopper can be classified into 5 parts. One is your class A chopper, that is called your one quadrant chopper because it in this quadrant the voltage and current both are positive. Then class B chopper, this is also a one quadrant operation. In this chopper, the voltage will be positive but current will be negative. Like this class C chopper, this is called a two quadrant operation. Class D chopper, which is also called a two quadrant operation, and class E chopper, this is called a four quadrant operation. So uh, based on the output voltage, chopper also classified in step up chopper and step down chopper and buck boost chopper. Okay. So direction of the current and voltage chopper can be classified into 5 parts: class A, B, C, D, and E. And according to your output voltage, is it step up or step down? According to output voltage, you can divide chopper into 3 parts. It may be your boost chopper, buck chopper, and buck boost chopper. Now, further classification of chopper. So, depending upon the power loss occurred during turn on and off of the switching devices, so the choppers are classified into two categories. Okay, so chopper can be classified into two categories. One is called your hard switched chopper. Here the and one another one is your soft switching chopper. In hard switching chopper, the switching losses is high, but in soft switching chopper, the switching losses is less. So, what is your switching losses? When you turn and turn off any switch, there will be some voltage and current which will appear across the switch. Due to this voltage and current which is appearing simultaneously across the switch, there must be some power losses. So, this is called your switching hard switching. So here the power loss is high during the switching on and off of the switch as a result of the non-zero voltage and current on the power switches. In soft switching or resonant converters, in this type of choppers, the power loss is low and at the same time of switching as a result of zero voltage and zero current on the switches. So this is your hard switching and soft switching. Now, what is your DC to DC converter technology? How it works, and what are the technique which we can apply in DC to DC converter technologies? So one is your linear regulators, switching regulators, and charge pumps. We can divide these technologies in 3 parts. So you can see from the table that in DC to DC converter technology comparison, these are your parameter. This is your linear regulator. This is your switching regulator. and this is your charge pump. So the efficiency of linear regulator is low, switching regulator is high, and charge pump is medium. If you come to the EMI noise, then EMI noise is less in linear regulator, it is high in switching regulators, and it is medium in charge pump. Next, when you come to your output current, that is your low to medium in your linear regulator. Switching, this is your low to high in switching regulator, and charge pump, this is your low. If you talk about your boost step up, so linear regulator is not applied, and switching regulator has can be applied in boost conversion or step up conversion. Charge pump is also can be used for boost conversion or step up the voltage. If you talk about step down, these conversion can be done in three technologies, which is a linear regulator, switching regulator, and charge pump. If you solution size, that the linear regulator is very small, switching regulator is large, and charge pump is in medium. So these are the different technology which can be compared by this table. Now let's come to the point, what is your method of control? Like if you want to convert from DC to DC conversion, and you want fixed DC to variable output voltage. So how can you get the variable output voltage from the chopper? So there are two methods. One is your pulse width modulation, and another one is your variable frequency control. So in pulse modulation, what we do, we take a pulse width for a particular time for which your switch will remain on, and it will remain off for that another particular time. So this is your pulse width modulation. So width modulation, the pulse width T on of the output waveform is varied, keeping chopping frequency fixed. Hence, uh, chopping period T constant means the total time period will remain constant, your frequency will remain constant, but you can change the T on time. So therefore, output voltage is varied by varying the T on time. So in the next waveform, I will show you that how can we control the output voltage by using pulse modulation method. And another method is your frequency control method. So in this method of control, the chopping frequency f is varied to keeping the T on and T off constant. Okay, so this method is also known as frequency modulation. So frequency modulation is obtained full output voltage. Range of frequency has to be varied and in a wide range. So this method produces harmonics in the output, and for large T of load it may be discontinuous. So you can see in the diagram that in the first diagram you can see that this is your pulse width modulation method, in which the waveform is turned on, you are applying pulse for a particular time T on, and for this time this is your T off time. And in another waveform, again you are turning on this uh, SCR for this particular time, and this is turning on off for this particular time. But in frequency control method, already have you seen that you have to keep the constant T on and T off is your constant. So you can't vary T on and T off. This will be fixed, and you are getting output voltage. When your thyristor is turned on, then you are getting the output voltage, and when your thyristor is turned off, then you are not getting any kind of output voltage. So your time period T is fixed in both uh, you know in both the condition, and you can if f is varied, then you have to keep the either T on or T off constant. So in this case, T on is your constant, T off is your varying. But if you talk about your pulse width modulation, the time period t will be fixed. You can change both t on and t off time. But in your frequency control method, you can change time period t, but you have to keep either t on constant or t off constant. So I think it is clear to you that the different methods for controlling the output voltage of chopper. Now let's come to the next point. What is the principle of operation of your chopper? So in this case, a switch is connected in series with the DC voltage source and load. And the switch can be a power transistor, an SCR, or a GTO gate turn off thyristor. The switch will actually ideal switch will offer zero resistance. Ideal switch will offer your zero resistance and infinite resistance and instantaneous switching. The switch can be turned on and turned off with the help of triggering circuit and commutating circuit respectively. Commutating circuit means the circuit which is used to turn off the SCR, that is called your commutating circuit. It can be turned on or turned off as desired at very high frequency. Now during the T on period, chopper is in on condition and load voltage is equal to source voltage versus. So during the T off period, chopper is off condition. Load current flows through the freewheeling diode. So we can check in the diagram. So as a result, load terminal are short circuited by freewheeling diode. So the load voltage is zero during T off period, and in this manner, a chopped DC voltage is produced across the load terminal. So from the T is equal to T on plus T off equation, it is clear that the load voltage depends on two factors. One is your supply voltage and the duty cycle of the chopper. Since the supply voltage is constant, so load voltage is governed by the duty cycle of the chopper. So you can say in the other words that the load voltage is dependent on two factors, T on and T off. Now let's come to the next point. Hence, it is concluded that the average load voltage can be controlled by varying the value of T on and T off in the following two ways. So, varying T on keeping the periodic time T constant. This is called constant frequency system. And variable frequency system keeping either T on constant, a varying T off, or keeping T off constant and varying T on. So output voltage is equal to T on upon T on plus T off into Vs. So you can retain this equation T on upon T into Vs, which is equal to alpha into Vs, where alpha is equal to T on upon T, which is called your duty cycle. So alpha is your duty cycle, which is equal to T on upon T, where T is equal to T on plus T off. So chopper frequency is F is equal to 1 by T. Chopper frequency means that how many times your switch will turn on and turn off. So this is your chopper frequency. So by switching on, turn on, turn off the switch, you can decide the switching frequency of a chopper. So this formula is very important because there are some few numerical which is asked, which is depends upon this formula in your exam. So keep this formula in your mind, okay? And this is very important that in numerical questions we can ask that what is the duty cycle of this particular chopper, and the T on and T is given, okay? So you can see in the diagram that uh, here one switch is connected to the DC voltage, and freewheeling diode is connected in parallel with your load. Series inductor is also connected. When this switch is turned on, the freewheeling diode will be in reverse bias. So the current will be carried by this, switch to load, and the cycle will complete. When your switch is turned off, due to this inductor, the freewheeling diode comes into the picture, and it become your forward biasing, and it will supply the load current through this freewheeling diode. So you can represent a chopper by this switch, where this is your DC voltage and you are getting DC output voltage over here. Now let's come to the step down chopper. So as you know, in the transformer we have already done that what is your step down transformer. So in a step down transformer, the output voltage is less than your input voltage. That was your AC voltage. Like this, the output voltage is less than input voltage in your step down chopper. This is also called your buck chopper. So the thyristor in the circuit acts as a switch. When thyristor is turned on, the supply voltage appears across the load. When thyristor is off, the voltage across the load will be zero. So practical arrangement includes an inductor L and a diode, which are used to eliminate the current pulsation, providing a smooth DC current. So with S closed, D is off and it remains off as long as S is in on condition. So the input current builds up exponentially and flows through L and load. So V output is equal to your V input. When switched off, the current through L decays to zero. This causes an inductive voltage which has opposite polarity across the L. So you can see that this is your buck circuit in which you are supplying your DC voltage through the pulses. Switch will remain on for a particular time. In that case, the diode will be in your reverse bias. So the current will flow through this path when your switch is closed. When your switch is open, the diode will be in positive direction and the current start flow through this particular loop. So this is all about your buck chopper. Now let's come to the waveform. You can see that when this is your output voltage, in this case the output voltage is less than your input voltage. So when you apply, this is your input voltage and this is your output voltage. You can see. So output voltage is less than your input voltage. When you apply, when you turn on the switch for this particular time t on, the output voltage will appear. Okay, the output voltage will appear and the current will start to flow. For this particular time t off, there is no output voltage. Okay, you are not getting any kind of output voltage, but you are getting current just because of inductor, and the current is flowing through the freewheeling diode. You can see in this diagram that the current is flowing through the freewheeling diode, and you can see that when the thyristor is on, supply voltage appears across the load. When thyristor is off, the voltage across the load will be zero. So when S is closed, D is off and it remains off as long as S is in on. So the input current builds up exponentially and flows through L and load. So output voltage is equal to VI, and S is off or open. The current through L decays to zero. Now let's come to the this is continuous current mode. So you can represent the load current by this equation. So load current is equal to I maximum plus I minimum. You can see from the diagram. that is your I maximum current, and this is your I minimum current. So total current is equal to I maximum plus I minimum, which is equal to I naught, which can be represented by V naught by R. Again, VL, this is your load voltage, which is equal to your output voltage, sorry, inductor voltage, which is equal to your output voltage, and the inductor voltage can be written L di naught upon dt. So V naught upon L tends to del I naught. So you can write this equation that the voltage across the inductor is equal to V naught upon L into delta T. This is your inductor current and this is your inductor voltage. When switch is open, when switch is open, so the peak to peak ripple current is written as delta I naught, which is equal to I max minus I minimum. You can see that when switch is open. Okay, so this current can be written as I max minus I minimum is equal to V naught upon LT off, because this is off for this particular time. In this particular time you are getting that much of current. Okay, so you can write the equation from this equation that I max is equal to IL minus I minimum. So V naught R is equal to plus V naught upon 2LT of, which is equal to I minimum is equal to V naught upon R minus V naught upon 2L into T of. Like this, you can find out the diode current, which is equal to I off when current which is flowing when your switch is off, and T on upon T period. So T on upon T can be written as D by small d. So this is your duty cycle. So I naught is equal to I upon D, which is equal to your, where D is equal to your duty cycle. Now step down chopper as element are ideal. So DC power drawn from source must equal the DC power which is absorbed. So from the diagram you can see all the waveforms are given over here. For this particular waveform, you can see that for this particular time your chopper is turned on, and you are not getting any output voltage across the diode, and there will be current which is flowing through the circuit, and there is your output current which is your I max and I minimum. And when switch is when switch is off, the diode will conduct and there will be current across that through the diode, and there is no input current and you are still getting your output current, and the voltage across the inductor is your negative in this case, but the direction of current will remain positive. So again you can turn on the SCR for this particular time and you can get the waveform like this. So this is your continuous current mode, because current is not getting zero in that case, and the output current is equal to I max upon I minimum, and input voltage is equal to your output voltage. Sorry, output voltage is less than your uh, input voltage. So for low value of D and low value of L, IL decreases and may fall to zero during turn off time. So it again builds up with T on, and hence it is called discontinuous mode. If you are taking your duty cycle, which is less, then the current may fall into at the 0 point. So this is called your discontinuous mode. So this is called your discontinuous mode. This is your step down chopper, which is your discontinuous mode, and these are the waveforms. So this mode is undesirable and is avoided by proper selection of chopping frequency. And the minimum value of L for continuous current mode is ensured by setting I minimum is equal to I naught. So I minimum is equal to V naught upon R minus V naught upon R T off, which is equal to 0. So T of you can get the value of L by solving this equation, which is equal to T of period divided by 2 into R. Now let's come to the different type of chopper, which is your type A chopper, type B chopper, type C, type D, and type E chopper. Let's come to the point type A chopper. So what is your type A chopper? Uh, Before going on this, we come to your step up or boost chopper. So the output voltage is more than the input voltage by several times. So L is used to provide a smooth input current. Now, the SCR acts as a switch which works in the PWM mode. When S is on, the L will be connected to the supply and the load VL jumps instantaneously to V1. But current through L increases linearly and it stores energy. When S is open, the current collapses, the energy stored in L transfer to C through the diode. So the induced voltage across the inductor reverses and adds to the source voltage into increasing the output voltage. So the current that was flowing through S now flows through L, D, and C to the load. So energy stored in the inductor is released to the load. So with S is closed again, D becomes in reverse bias and the capture energy supplies to the load voltage and the cycle repeats. So V naught is equal to Vi plus VL. So V naught is always higher than input voltage because the polarity is the same of VL is the same your input voltage. If inductor is L is very large, then the source current is ripple free and is considerably constant and assuming capacitor to be large enough to neglect the voltage ripple. So output voltage is considered constant. Since losses are neglected, the energy transfer during T off by L must be equal to the energy gain during T on. So in ideal case, the energy which is transferred to the inductor is equal to when you turn off the thyristor and it is transferring from the inductor to the source. So the output voltage is always greater than to your input voltage. Now you can see the equations which is here and the waveforms for your boost chopper. So input power is equal to output power, which is equal to V1 I1, which is equal to V naught square upon R. And from this waveform, you can see that for this particular time, chopper is your turned on, and for this time, your diode is turned on. So the switch current is flowing when switch is on. When switch is off, diode is on, the current is flowing through the diode, and you are getting the waveform of this voltage is this. And this is your output voltage, which is your higher than your input voltage. So from the equations, you can see that the output power is equal to input power. So V1 I1 is equal to V square upon R and I1 is equal to V1 upon 1 minus D square into 1 by R and inductor current is equal to I max plus I minimum divided by 2 which is equal to your I1. And the voltage across the inductor is VL is equal to V1 which is equal to D which is equal to LDI upon dt and you can see from this equation you can get di1 dt is equal to v1 upon L. So del I1 is equal to v1 upon L into T on or I maximum minus I minimum, and you will get V1 upon L into T on. Again, I maximum plus I minimum is equal to 2 into I1. So solving these equations, finally you will get that I max minus I minimum is equal to V1 into T on time upon L. So for continuous current mode, IMI is equal to 0, and uh, the I minimum can be written as by this equation. Now, this is your, R into 1 upon 1 minus D square is your turn on upon 2L. So by this equation, you can easily get the value of your inductor. Now, buck boost chopper. So it is your combines the concept of both the step up and step down choppers, and the output voltage is either higher or lower than the input voltage. The output voltage polarity can also be reversed. The switch is either on an SCR or GT or IGBT. When switch is on, D is in reverse biased and ID is 0. The voltage across L is equal to the input voltage, and the capacitor supplies energy to the output load. The current through the inductor increases linearly with time. With S off, the source is disconnected and the current through inductor does not change instantaneously, and it forward biased the diode, so providing a path for the load current, and the output voltage becomes equal to the inductor voltage. So this is the your buck boost chopper. We have already done with buck converter and boost converter. In buck converter, your output voltage is uh, less than your input voltage, but in boost converter your output voltage is higher than your input voltage. But in buck boost converter, you can get input voltage less than to the your input voltage, and the output voltage is higher to the input voltage. So both the chopper when combined, that is called your buck boost converter. So you can see in the picture or in the diagram that there are two voltage, there are DC source, and a series switch is connected to this DC source, and there is a diode, uh, and one is your capacitor and another one is your load. Another one is your load, and when switch S is your on, when switch S is on, then the power which is transferring, which is equal to V1 into I1 into T on time period. When S is off, the power which is transferring is equal to V1 into I1 into T off period. So ignoring losses, T on and T off is equal to V1 into I1 into T on is equal to V1 into I1 into T off. And output voltage is V1 into dt upon 1 minus d into t is equal to V1 d upon I minus d into output. Output voltage is controlled by changing the duty cycle d. So inductor current is equal to I max plus I minimum is equal to 2, and I1 is equal to IL into d. So you can get this equation for the buck boost chopper. By further solving this equation, you can get the output power is equal to V naught square upon R, and I max is equal to, you can get from your minimum current. So you can get a minimum induction. I minimum is equal to 0. So the inductor value must be equal to RTD upon 2 into 1 minus D square. Now, so this is all about your buck boost and buck boost chopper. Now we come to the some you know MCQs which is based on this chopper. In the next lecture, we will discuss about your class A chopper, class B chopper, or class C chopper, and class D chopper. So let's come to the some questions, some basic questions. So these are the MCQs which is based on this lecture. So first question is this, that the in the type of chopper, two-stage conversion takes place. If you are using AC link, then you need two-stage conversion. First, you have to convert DC to DC, and for AC link, then you have to convert this DC to AC. Okay. Next is your choppers convert. So chopper always convert DC to DC, fixed DC to variable DC. A chopper may be thought as a inverter with DC input, DC equivalent of an AC transformer, diode rectifier, DC equivalent of an induction motor. So I have already told you that the chopper will behave like a AC transformer, which is your DC equivalent to AC transformer. Next is your which device can be used in a chopper circuit. So as a chopper circuit, as a switch, you can use BJT, MOSFET, GTO, any kind of semiconductor device which you can as a switch. Now the fifth question is, a chopper is a time ratio controller, AC to DC converter, DC transformer, or high speed semiconductor switch. So chopper is your high speed semiconductor switch. Now, what is the duty cycle of a chopper? So duty cycle of a chopper is turn on time upon divided by T. So this is your duty cycle of your chopper. Now next point is your the load voltage of a chopper can be controlled by varying the duty cycle, firing angle, reactor position, extension angle. So the load voltage of the chopper can be controlled by varying your duty cycle. Now the values of duty cycle lies between uh, 0 to 1 means the alpha is less than greater than 0 but less than 1. Alpha is greater than less than 0 but greater than minus 1. Alpha is less than or equal to 0. Alpha is greater than or equal to 0 but less than or equal to 1. And alpha is less than 1 and is less than greater than 1 but less than 100. So alpha's maximum value is your 1. So C is the right answer for that. That alpha may be your equal to 0 or greater than 0, but it it is always less than or equal to 1. Next question is, T is the time period for a chopper circuit and alpha is its duty cycle, then the chopping frequency is. So we have already told you that the chopping frequency of your chopper will be alpha upon turn on time. By this formula, you can easily calculate the chopping frequency of the chopper. Next question is here, find the output voltage expression for the step down chopper with Vs as the input voltage and alpha as the duty cycle. So you can calculate the output voltage for a step down chopper by using this formula, which is equal V naught, in which V output is equal to Vs into alpha. So this is all about your chopper, in which we have done that chopper is a DC to DC converter. By varying duty cycle, you can change the output voltage. It may be classified into three parts. It may be your buck converter, buck chopper, boost chopper, and your buck boost chopper. In in buck chopper, your output voltage is always less than your input voltage. Your boost chopper, your output voltage is always greater than your input voltage. And in buck boost chopper, both operations can be done. It may be your step down or it may be your step up, and it behave like your transformer, which work in AC to step up or step down the voltage. So it is identical your transformer. And all the thing which is depend on your duty cycle of the chopper. And high speed as a we perform as a high speed switch. So this is your all about your chopper. In the next lecture, we will discuss about class A chopper, class B chopper, class C chopper, and class D chopper, and class E chopper. So, thank you.